Light does not exist until you look at it. I know that sounds like something a fortune cookie would say, but I am a physicist, and I am telling you this is what the experiments show. The most carefully tested theory in the history of science says that light, the stuff streaming through your window right now, does not have a definite reality until the moment it is observed. That is not poetry. That is physics. And by the end of this talk, you will understand exactly what I mean. It will change how you see the world, literally. Let me start with something that puzzled me for years. A photon, a particle of light, has no mass, zero, nothing. And yet, if you shine a flashlight at a tiny piece of foil hanging from a thread, the foil moves. Light pushes it. Light has momentum. But wait. You learned in school that momentum equals mass times velocity. If the mass is zero, the momentum should be zero. The foil should not move. But it does. How can something with no mass push things around? Here is the answer, and it is beautiful. Newton's formula works fine for baseballs and cars, but it is incomplete. Einstein gave us the full picture. Energy and momentum are connected in a deeper way. The complete equation is this: energy squared equals momentum squared times the speed of light squared, plus mass squared times the speed of light to the fourth power. Do not panic. Here is what it means. For anything with mass, some of its energy is locked up in that mass. That is the famous E equals mc squared part. But for a photon, the mass is zero. So all of a photon's energy comes from its momentum. A photon is pure motion. It cannot sit still. It must move. And that motion is its entire existence. This is not just mathematics. In 1923, Arthur Compton shot X-rays at electrons. The X-rays bounced off and lost energy exactly as if they were little balls colliding with the electrons. The photon transferred momentum to the electron and recoiled with less energy. We measured it. The numbers matched perfectly. Light has no mass, but light has momentum. Light can push things. That is strange, and we are just getting started. Now, you learned in school that light is a wave, and you had good reason to believe this. Here is the proof. Take a barrier with two thin slits. Shine light through. What do you see on the wall behind? If light were made of tiny bullets, you would expect two bright stripes. Bullets go through the left slit, hit the wall, make a bright spot. Bullets go through the right slit, make another bright spot. Simple. That is not what happens. Instead, you see a pattern. Bright bands, dark bands. Bright bands, dark bands. Stripes, like a zebra made of light. This is interference. Only waves do this. When two wave peaks meet, they add up. Bigger wave. When a peak meets a trough, they cancel. Nothing. The bright bands are where light waves add together. The dark bands are where they destroy each other completely. Case closed. Light is a wave. But a wave in what? Water waves need water. Sound waves need air. What is light waving through? The old scientists had an answer. They invented something called the luminiferous ether, an invisible substance filling all of space. Light, they said, ripples through this ether like sound ripples through air. Then came the experiments. People tried to detect the ether. They failed. There is nothing there. Empty space is actually empty. So what is doing the waving? In the 1,860 seconds, a Scottish physicist named James Clerk Maxwell discovered something extraordinary. Electric fields and magnetic fields are not separate things. They are dance partners. They create each other. Wiggle an electric charge up and down. The changing electric field creates a magnetic field. But now that magnetic field is changing too. And a changing magnetic field creates an electric field, which creates a magnetic field, which creates an electric field. The disturbance leapfrogs through empty space, sustaining itself, racing forward. Maxwell calculated how fast this ripple would move. He got 300,000 kilometers per second, the exact speed of light. Light is not a wave in any substance. Light is a wave of the electromagnetic field itself. Invisible electric and magnetic fields dancing through the void. And that speed, 300,000 kilometers per second, is not just how fast light happens to travel. It is built into the fabric of reality. It is the exchange rate between space and time. Einstein showed us that space and time are woven together into one thing, space-time, and the speed of light is what tells you how to convert between them. 1 second of time is equivalent to 300,000 kilometers of space. That is the conversion. That is why nothing can go faster. It is not a speed limit posted by the universe. It is a fundamental feature of space-time geometry. Good. So light is an electromagnetic wave. We understand what it is waving. Mystery solved. Except it is not solved, because now I am going to break everything. Around 1905, a young man named Einstein was puzzling over something strange called the photoelectric effect. Shine light on a piece of metal, electrons pop out. Simple enough. Light carries energy. The energy kicks electrons free. They fly off. But here is the problem. Red light does not work. You can blast a metal surface with the brightest, most intense red light imaginable. Nothing happens. No electrons. Crank up the power. Still nothing. Leave it on for a year. Nothing. But shine a dim blue light, barely any light at all, and electrons immediately start flying off. Think about how strange this is. If light is a wave, a brighter wave carries more energy. Enough red light should eventually knock electrons loose. But it does not. Einstein figured it out. And his answer changed everything. Light does not deliver energy smoothly, like a wave washing over the shore. Light delivers energy in packets, little bundles. We call them photons. And here is the key. The energy of each packet depends on the color. Blue light has high energy photons. Red light has low energy photons. Think of it like this. Imagine you are trying to knock a coconut off a stand at a carnival. You can throw 1,000 ping pong balls at that coconut. Throw them all day. The coconut is not moving, but one well-thrown baseball knocks it right off. Blue photons are baseballs. Red photons are ping pong balls. It does not matter how many ping pong balls you throw. Each one is too weak, so light comes in particles. Little bullets of energy called photons. But wait. We just proved light is a wave. The interference pattern. The stripes. Waves cancel. Particles do not cancel. What is going on? Here is where I must be honest with you. Light is not a wave. Light is not a particle. Light is something else entirely. Something that does not exist in everyday experience. It behaves like a wave when you ask wave questions and like a particle when you ask particle questions. This is not a failure of our understanding. This is what light actually is. Let me show you how strange this gets. We set up the two-slit experiment again, but this time we turn the light way down, so dim that only one photon passes through at a time. One little packet of energy. We wait. Then another. We wait. Each photon hits the detector and makes a single dot. One photon, one dot. Nothing strange there. We keep going. Thousands of photons, one at a time. Now, if each photon is a particle, a little bullet, it has to go through one slit or the other, right? So you would expect the dots to pile up in two clusters, one behind each slit. That is not what happens. The dots build up into the interference pattern. Bright bands, dark bands, the same striped pattern you get when you send a continuous wave through. But we sent them one at a time. How does a single photon interfere with itself? How does it know where the dark bands are supposed to be? Here is the answer, and I want you to sit with how strange it is. The photon does not go through the left slit. It does not go through the right slit. It does not go through both slits. It does not take any definite path at all. Instead, there is something called a probability amplitude. Think of it as a mathematical wave that describes where the photon might be found. This amplitude goes through both slits at once. It interferes with itself, just like a water wave. And then, when the photon hits the detector, it appears at one specific spot. The photon does not have a position until it is detected. Before that, asking which slit it went through is like asking what a coin shows before it lands. The question has no answer. Not because we do not know, because there is no answer yet. Now, let me tell you something I spent years working on. It is called the path integral, or the sum over histories. And it reveals something even more surprising about light. When a photon travels from point A to point B, how does it get there? You might think it takes the shortest path, the straight line, the obvious route. It does not. The photon takes every possible path, all of them. At the same time, some paths are straight. Some paths zigzag wildly. Some paths loop around the moon and come back. In the mathematics of quantum mechanics, every single one of these paths contributes to what the photon does. Now, here's the trick. Imagine that as the photon travels along each path, it carries a little spinning clock. The hand of the clock rotates at a rate determined by the photon's wavelength. When we calculate what happens at point B, we add up all these little clock hands, one from each path. What do we find? The paths near the shortest route all have their clock hands pointing in roughly the same direction. They add up. They reinforce each other. But the crazy paths, the ones that loop around wildly, have clock hands pointing every which way. They cancel out. So even though the photon explores every possible path, the crazy ones cancel and the sensible ones survive. That is why light seems to travel in straight lines. But it is an illusion. Underneath, every path is being explored. Let me give you a concrete example. A mirror. In school, you learn that light bounces off a mirror with the angle of incidence equal to the angle of reflection. Simple, sensible, but here is the truth. Light bounces off every part of the mirror, at every angle. The parts far from the middle, they contribute too, but their clock hands point in all different directions and cancel out. Only the paths near the center, where the travel time is almost the same, add up. Here is the magical part. If you take a mirror and scratch away the parts where the clock hands point in the wrong direction, carefully, at just the right intervals, you can make light bounce off the edge of the mirror, a place where it normally would not go. You have made a diffraction grating. The crazy paths no longer cancel. Light goes where it should not. The photon does not know physics. It does not calculate the shortest path. It explores everything, and the math does the rest. Now let me push you even further down the rabbit hole. Suppose you want to catch the photon in the act of going through one slit. You put a tiny detector at each slit, something that tells you left slit or right slit. What happens to the interference pattern? It vanishes. Gone. Destroyed. Instead of stripes, you get two blobs, one behind each slit, exactly what you would expect for particles going through one slit or the other. The moment you ask which path the photon took, it starts behaving like a particle. It goes through one slit, not both, and no interference. This is not because your detector bumped the photon. You can make the measurement incredibly gentle. It does not matter. Any interaction that reveals which path destroys the interference. Now let me tell you about an experiment that will twist your mind further. It is called the delayed choice experiment, proposed by John Wheeler. The photon goes through the two slits. It is flying toward the detector. But before it arrives, you make a choice. Either you leave the detector alone and get the interference pattern, or you suddenly insert something that tells you which slit the photon went through. Here is the strange part. You make this choice after the photon has already passed the slits, after it has already decided whether to go through one or both. What happens? If you choose not to measure the path, you get interference. If you choose to measure, you get two blobs. But the photon already went through the slits. How can your later decision affect what happened earlier? The answer is unsettling. The photon did not do anything until you measured it. There was no fact about its path, not even in the past. The history of the photon is not determined until the experiment is complete. This is not time travel. This is not the future changing the past. But it is telling you something profound. The past is not as fixed as you thought. At the quantum level, what happened depends on what you choose to measure now. Now let me tell you what light is at the deepest level we understand. Imagine that all of space is filled with an invisible ocean. Not water, not ether, the electromagnetic field. This field exists everywhere. In the emptiest void between galaxies, it is there. Here is the strange part. Even when there are no photons, even in complete darkness, this ocean is never perfectly still. Why? Because of the uncertainty principle. You cannot know both the position and the momentum of a particle with perfect accuracy. But this applies to fields too. You cannot have an electromagnetic field that is perfectly, exactly zero everywhere. That would be too precise. The universe does not allow it. So the field constantly shimmers, tiny fluctuations, little ripples appearing and disappearing too fast to see directly. We call this the quantum vacuum. These are not photons in the usual sense. We call them virtual particles. They flicker in and out of existence, borrowing energy from nowhere for the briefest instant, then paying it back. You might think this is just mathematical bookkeeping, but these vacuum fluctuations have real, measurable effects. Here is one. Take two metal plates. Put them very close together in a vacuum. A tiny gap, smaller than the width of a human hair. Something strange happens. The plates are pushed together by nothing, by empty space. This is called the Casimir effect, and here is why it happens. Outside the plates, the vacuum fluctuations can have any wavelength, any size ripple, but between the plates only certain wavelengths fit. Wavelengths larger than the gap are suppressed. There are fewer fluctuations inside than outside. This creates a pressure imbalance. The vacuum pushes the plates together. We have measured this. It is real. The force is tiny, but it is there. Empty space is not empty. It pushes on things. Here is another effect. Inside a hydrogen atom, the electron orbits the nucleus. According to one calculation, two particular energy levels should be exactly equal, but they are not. There is a tiny difference, about 1 part in a million. Why? Because the electron interacts with the vacuum fluctuations. The shimmering of empty space slightly changes its energy. This is called the Lamb shift, and we have measured it to extraordinary precision. Our predictions match the experiments to 12 decimal places. These vacuum fluctuations also explain something mysterious: spontaneous emission. An atom in an excited state eventually drops to a lower energy and emits a photon. But what triggers it? If the atom is alone in empty space, what makes it decide to emit? The vacuum fluctuations. The constant shimmer of the electromagnetic field tickles the atom. It is like a gentle nudge that eventually tips the atom over the edge. Without the vacuum, atoms might stay excited forever. So, what is a photon, really? A photon is not a thing that moves through the electromagnetic field. A photon is an excitation of the field itself. A ripple. When we say there is a photon, we mean the field in that region is vibrating in a particular way. Think of a stadium wave. People stand up and sit down, and the wave moves around the stadium. But no person travels around the stadium. The wave is just a pattern moving through. A photon is like that. It is the electromagnetic field doing a particular dance, and that dance moves through space at the speed of light. When that ripple reaches your eye and hits a molecule in your retina, the dance transfers its energy to an electron in that molecule. The electron jumps to a higher energy level. The ripple is gone. A signal goes to your brain. You see, the light from a distant star began as electrons jiggling on that star's surface. Those jiggles set the electromagnetic ocean rippling. The ripple traveled across space for years, centuries, sometimes billions of years. Then it entered your eye, jiggled an electron in your retina, and you saw a star. You are connected to that star by this invisible ocean. Now, how do charged particles push and pull each other? You know that two electrons repel. Two opposite charges attract. But how? They are not touching. How does one electron know the other is there? In quantum electrodynamics, the answer involves virtual photons. The electromagnetic field between the charges is disturbed. These disturbances carry momentum from one particle to the other. But be careful. Virtual photons are not tiny balls being thrown back and forth. That picture causes confusion. It is better to think of the field itself as being perturbed, and the perturbation carrying the force. The mathematics of how these perturbations add up determines whether the force is attractive or repulsive. It depends on the charges involved. Opposite charges attract. Like charges repel. The virtual photons do not know anything. The math of interference determines the outcome. Now, why should you care about any of this? Because it tells you something profound about reality. We evolved to find food and avoid predators. Our brains are built for rocks, trees, faces, and weather. We expect the world to be made of solid objects with definite positions and predictable paths. But when we look carefully, with precise experiments and honest mathematics, we find something else. Reality is not made of little solid things. It is made of fields and fluctuations, patterns and probabilities. The universe does not play by the rules we assumed. And light, the most familiar phenomenon in existence, the first thing you ever saw, is the doorway into this deeper reality. Every time you see anything, photons are entering your eyes, little quantum excitations of an invisible field filling all of space. They do not have definite paths until they arrive. They explore every possibility. They are affected by vacuum fluctuations shimmering in empty space. You are not seeing a solid, fixed world. You are seeing the universe revealing itself to you, one quantum event at a time. When you look at a sunset, you are seeing different frequencies of the electromagnetic field triggering different responses in the molecules of your eye. When you look at the stars, you are receiving messages that have traveled longer than humans have existed, ripples that began in nuclear fires, crossing the void, ending in your eye, in this moment. The universe is connected by this invisible ocean of light. And the most wonderful thing? We can understand it. Not completely, not yet, maybe never completely. But we can ask questions, and nature answers. We can do experiments, and the results make sense. We can write equations, and they work sometimes to 12 decimal places. The universe is not required to be comprehensible, but it is. And that fills me with something I can only call joy. So what is light, really? Light is a quantum excitation of the electromagnetic field. It is neither wave nor particle in the old sense. It is something new. Something that required us to invent new mathematics and new ways of thinking. Understanding it opened the door to lasers, computers, medical imaging, and 1,000 technologies we take for granted. But more than that, understanding light showed us that reality is stranger and more beautiful than our ancestors could have imagined. And we are just getting started. Thank you for listening. Now tell me in the comments, what surprised you most about the nature of light?